The gravity is still non-unified with the quantum theory, but there's some topics of the gravity theory to combine through with the quantum field theory. We talk about some several topics from the gravity theory, starting from the weak gravity conjecture, so-called the WGC, and the black hole super-radiance, PHSR, and finally I want to talk about the digits and the anti-digits pies. So first of all, the weak gravity conjecture WGC is the gauge interaction or gauge force. Its strength should be stronger than the gravity. This can be written as the following inequality: the charge to mass ratio Q of m should be larger than the 1, or equivalently, m is less than the c times the Planck mass. Here's the left inequality. The Planck mass is said to be the unity, just the 1. Here, how can we interpret it as the right hand side? This represents the strength of the gravity. So the Hilbert actions can be written like the following: boom. Here, this R is corresponding to the Riemann curvature tensors of the general relativity theory, and the kappa is represented by the Newtonian gravitational constant. So here's the kappa is 4 pi z, 1 over the 4 pi z, and this is the same with m Planck scale. So by the dimensional analysis, either the consistence, there's mass scale dimensions in the Planck mass and the mass scale dimensions in the Riemann curvature tensor due to the secondary derivatives of the matrix. And the gauge force part can be written as the field strength, and the coupling is given by one of the scales. So that we can compare the strength of the two interactions, the gauge interaction and the gravitational interactions, with the two terms. One is the Planck masses, and the other one is the gauge coupling. So here's the gauge coupling is given by the one of the z, and here's the Planck masses is correspond to the gravitational interaction strength. So for stronger gauge forces, in the direction of the inequality is the following, and by the dimensional analysis there is the mass case here. So the 1 over the m Planck scale is less than the coupling constant scales over the mass. So this is a statement through the weak gravity conjectures, and such a weak gravity conjectures gives the lower bound of the specific gauge interaction coupling, unlike the experimental or measurement give the upper bound on the gauge coupling. Such a weak gravity conjecture is equivalent to the other statement. The first one is there is no exact global symmetry in the quantum gravity. The magnetic version of the weak gravity conjecture is following: the effective field theory cutoff, the capital lambda scale should be smaller than the c times the Planck mass. And if we consider the coupling G go to the zero limit, then the effective field theory cutoff lambda also goes to the 0. So effective field theory breaks down. So to block the G go to the 0 limit, the gauge symmetry, which is represented by the gauge coupling Z, can not become the exact global symmetry. So because G equal 2, limits of the gauge symmetry correspond to the global symmetry, so the such a G go to 0 limit should not be occurred. So in the quantum gravity theory, there is no global symmetry. This is equivalent statement with the weak gravity conjecture. The other equivalent conditions of the WGC is the black hole decay. We can consider the charged black hole, so-called Leissner Nordstrom black hole with the specific electric charge Q. There are two horizons, R plus minus, represented by the black hole mass, capital M, and the electric charge, capital Q. And by the black hole decay, the small m and the small q is emitted. And to guarantee the stability of the horizon, still the insides of the root should be the rather than the zero. So this inequality should be holded. And if we assume that the initial condition satisfy the externality, which is that the inside of the root is exactly zero, then such emissions of the small m and small q is possible kinematically if and only if under such a condition. And such a Newtonian gravitational constant can be replaced by the Planck mass, and this is the same conditions with the weak gravity conjunctions. In the points of the quantum gravity, there are two regions of the theory. The one is the landscape, and the other one is the swampland. The landscape is a low energy effective field theory, which arises from the UV quantum gravity. So if there's energy scale in the UV theory, the quantum gravity lives in this scale, and by the evolving and integrating out through the effective field theory approach, then there's a low energy effective field theory. This is called the landscape. But there's a swampland. The effective field theory looks like this is fine for the ordinary gravity rule. There's a very good properties like the unitarity, locality, or symmetry, and so on. But this is not completed in the quantum gravity theory. So some low energy theory cannot live through with the gravities in the UV scale. So the WGC is one example of the swampland. Like as a black hole decays or the no global symmetry. And if you use some new effective theories fail to satisfy the WGC, then it is in the swampland. But if the effective field theory still satisfies the WGC, but it does not guarantee that theory is in the landscape. So such a WGC is just a practical test. The effective theory whether it belong in the swampland or not, but it does not guarantee to belong in the landscape. Now on turn to the second topic of the today's video. The second topic is a black hole super-radiance. Already I said the black holes are decay and it loses the energy, spin, or electric charges. The black hole has only the three physical quantities. This is called the no-hair theorem: mass, charges, and the spin. In the previous topics, we discussed the mass and the charges, but here now we will discuss the mass and the spin, so-called the curved black hole. And the black hole super-radiance is the loss of energy and the spin by the super-radiance, and this forms a scalar cloud as a bound state, and this is similar to the atomic bound state. There are some detailed conditions for this BHSR. We can set some several parameters of the black hole, like the gravitational radius, spin parameters A star, and the horizon angular velocity capital omega h of the black hole, which is given by the black hole masses and the black hole angular momentum. And the birth conditions of the black hole super-radiance is given by the following inequality. The scalar mass. So there's a black hole, a rotational black hole, and around that there's a scalar field. That scalar field mass should be smaller than the angular velocity through the black hole. And the second condition can be written through with the black hole spin down if the black hole spin difference is a delta I star, and the condition is associated through with the gross light of the scalar field around the black hole, so that we can set the occupation number of this scalar clouds as the capital NM. And the gross light of the scalar cloud can be written as such a gross light form with some dimension analysis. And the time scales of the black hole, for example, the lifetime or characteristic time scale of the black hole should be the smaller. This I mean the gross light of the scalar light, and we can calculate the some time scales of such a gross light. This is smaller than the characteristic time scales of the black hole with the additional factors of the Ln of the Nm, and this can be reduced in the following conditions. So there are two conditions for the black hole super-radiance, and by combining that, we can obtain the excluded mass ranges of the specific scalar field, especially the ultralight dark mass ranges. If we use the different information of the black hole, the first one is stellar black hole, so like has 10 times of the solar mass. The excluded mass range of the ultralight dark matter is the 10 to the minus 22 to the 10 to the minus 11 electron volt. And if we use information of the supermassive black hole, like the MBH with the 10 to the 6 to 10 to the 9 solar mass, then the excluded mass range is given by the 10 to the minus 20 to the 10 to the minus 16 electron volt. So this plot represents the black hole super-radiance, how the black hole super-radiance excludes the ultralight dark matter mass range. So this blue data correspond to the stellar black hole, and this orange data correspond to the supermassive black hole, and the x-axis is the ultralight dark matter mass ranges, and the black curves correspond to the probabilities of the excluded exclusions of the ultralight dark mass. So in this mass range and this mass range is the excluded, and such excluded exclusion probability is related with the black hole spin, and this mass range is proportional to the black hole mass by using such a VHS conditions. The final topics of the today is the digital and anti-digital space. Briefly, such a digital and anti-digital space is a maximal symmetric solution of the Einstein field equations of the general relativity theory with the cosmological constants capital lambda. If the capital lambda is positive, it means that the curvature is positive and corresponds to the digital space, and if the capital lambda is negative, corresponds to the negative curvature, and that is called anti-digital space. There are several ways to express the digital matrix with the choices of the coordinate system. They are all equivalent physically, but there's just a coordinate choice with the diffeomorphism of the general relativity theory. So this is the expanding universe, coordinates, partially flat, hyperbolic, and the cosmological horizons one. Similarly, we can make the anti-digital representation. So and there is anti-digital space and the safety correspondence. Some anti-digital space with the d-dimensional space-time is correspond to the conformal field theories in the d-1 dimension. So if there is an anti-digital space, the boundary of the anti-digital space is correspond to the conformal field theory. The well-known example in the string theory is the direct product of the 5-dimensional anti-digital space and the 5-dimensional space. This there's a correspondence with the unequal ball. This is called the number of the supercharges, super Young-Mills theory. This is the supersymmetric theory. Or there's also another example of such IDSFT, such a form, which is based on the boundary circumpermeability theory. So again, that is based on maximally symmetric solutions. The Riemannian curvature tensors correspond to the the proportional to the multiplication of the metric tensors, and it has the largest possible number of scaling factors, which represents the symmetry still in the space-time. In the cosmological point of view, such as the digital space is the possible approximations for the impulsion or light-time accelerations with the dark energy dominant, because these two are represented by the cosmological constant, and they also gives exponentially expanding solutions. So today we discussed the three topics in the gravity theories with a little combinations of the quantum theory. The first one is the weak gravity conjectures. The gauge force should be stronger than the gravity, and this can be represented by the charge to mass radius inequality. And there are equivalent conditions like the exact global symmetry and gravity theory or black hole decay statement, and such a WGC is the good task to the specific build deal with this in the swarm plans or not, but not guarantees they belong in the landscape. And second, we discussed the black hole super-radiance, how the black hole's energy spin loss can exclude the specific mass ranges of the dark matter. And finally, we discussed briefly the digital and anti-digital space and some point tips of ADS and the cosmological view.